Alrighty, hello everyone. We are on page 11, so make sure you're following along with me, taking notes as we go. Now, the important part of this topic is recognizing that these are weak acids and weak bases. That last class we were specifically dealing with strong acids and strong bases. And what's really nice and convenient about having a strong acid or a strong base is that whatever the moles or the concentration is of a strong acid or a strong base, it will equal the moles or the concentration of H plus or OH minus, depending on if it's an acid or a base. That is not the case when it's a weak acid or a weak base. That means that if I have like a weak acid, so here's an example. This is a weak acid, and it's placed in water, right? It's aqueous. Not all of that weak acid breaks apart. So another way of writing this that I almost like better is here's my weak acid, and it aqueous, like dissolved in water, but not all of the H pluses are going to break apart from that. We're going to have this back and forth where some of the H plus is there, and then we still have a whole bunch, and there'll be a whole bunch of NH3 aqueous, right? Can you see that, where NH3 plus another H plus would give me NH4 plus, and we have this back and forth where all of this doesn't break apart into these things. These things can go back to that, and some of this can just be remaining there. And so if we do a K value, which would be products over reactants, again, we see how hydronium can be replaced for H plus. And the reason why this liquid is not in there is because we don't have liquids or solids in our K expressions. Alrighty, now like I told you, for strong acids and or strong bases, they completely break apart. That means that this HCl, it's not this reversible reaction where this is coming back and making more of the acid, and not all of this dissociates into those things. It completely dissociates. These things will completely form those. And just like before, we don't have to show this like water liquid. Another way of looking at this is here's my strong acid, and it will one-way arrow completely break apart into H plus and Cl minus. Okay? Those ones are aqueous ions. And again, if I write a K expression, the subscript of A just means acid. So it's like an acid dissociation. I have my products over my reactants. I don't include solids or liquids in those. And so again, we can see how H plus can always be exchanged for H3O plus. So if the K value is larger, that means that we have more of this item that broke apart into these, that we have a larger amount of H plus. So the larger the K value, the stronger the acid is. And then this is something I saw quite a bit today when we were visiting. Strong acid, something to make something acidic, it means that there's more H plus present in it, and it means that the pH will be lower. The lower the pH, the more H plus there is, and the stronger the acid. So if I look at this, here's my Ka values, and this is the largest Ka, this is the smallest Ka. So this would be my strongest acid, this would be my weakest acid. And if I were to write pHs, this would be my smallest pH, and this would be my biggest pH. So the larger the Ka, the larger the Ka, the stronger the acid, the lower the pH. Something you're about to see in a moment is a pKa, okay? And pKa's, now remember, the lowercase p just means negative log. So negative log of Ka. So similar to pH, this is the negative log of H plus. All right, this is what I want to show you. Let's do a little table right here. So we're going to have Ka, pKa, and then pH. Okay, so if we have a bigger Ka value, that means that we have a lower pKa and a lower pH. And this would, let's do one more strength of like this acid, right? This would be stronger. If we have a small Ka value, this would be a higher pKa, this would be a higher pH and a weaker acid. Understanding these relationships are going to be really helpful. It'll help you answer certain questions just really quickly. Same idea here for a weak base. So a weak base will gain H plus from water. Like that's what a base is. It's a proton receiver. So that's why we have to have water actually in these base reactions when we lay them out in the equilibrium. The acids we didn't have to. So bases receive hydrogens, and where they receive hydrogens is from the water. So that means if this gains a hydrogen, the water loses it, and then this becomes an NH4+. Okay, where for a strong base, we don't have to lay it out that way, which is nice. A strong base like NaOH, those can simply break apart into Na plus OH minus, and all those are aqueous. But when it's a weak base, we often have to have the water to show it as a proton receiver here. So reminder, liquids and solids are not in K expression, so we're going to do our products over our reactants there. They all have coefficients of 1 here, and so they're raised to the first. And so similar to before, when our Kb, when this value is really big, then there's a lot of hydroxide in there. That's a stronger base. So the larger the Kb, the stronger the base. You could have that same idea that we talked about before, that if we have a large Kb, that would have a pKb would be lower, and then, because I'm just focusing on this big one right here, so then our pOH would be lower, and our pH would actually be higher. The lower the pOH, the higher the pH, and that is a strong base, stronger base. And then this is just showing that relationship again, that pKa or a pKb is the negative log of Kb. And just from before, if you are given pKa, you can do 10 raised to the negative pKa, and that will equal Ka. So for this quick example here, pKa for this thing, now, first thing I notice is it's an acid, it has hydrogen at the front, but it's not one of my big 6, right? So this is a weak acid. And it says that the pKa is equal to 9.31. And we want the Ka. Well, if Ka is going to equal to 10 raised to the negative pKa. And remember the weird thing with the sig figs from before? When it was like pH and concentration there. So P values, whether it's pH, pKa, pOH, the first digit is not a sig fig. So this is actually only a 2 sig fig number. So when I plug this into my calculator, I'm going to just have an answer that's 2 sig figs, 4.9 times 10 raised to the negative 10. And then K values are unitless, just like pKa's and pH's. They're not concentrations. Okay, now these are the kinds of questions that you're going to see the most often. So we're going to do both of these questions. You're going to often be asked to solve for pH or pOH of a weak acid or a weak base. So the most important thing is that you need to recognize if it's a strong acid or a weak acid. Because guess what? HF is not on our list of big six. This is a weak acid. If it was a strong acid, then it would have made our lives so much easier, because then we would just say, well, if this is the concentration of HF, then that's the concentration of H+. And to get pH, we'd do the negative log of that concentration of H+. But because it's weak, that means we have this equilibrium. We have this back and forth between them. And so the only way to figure out what the amount of hydronium or H+ is to do an ice table. Now, we can include the liquid in here, but let's try this other reaction. Remember the one where it's just like HF aqueous, and then it's going to, and it's weak, so we get this like equilibrium, but it's going to break apart into H+ aqueous and F- aqueous. And because it's equilibrium and I want to know what's going on with H+ at equilibrium, I'm going to do an ice table. All right, great. Find the pH of 2.5 molar. Now, reminder, ice tables can be pressures or concentration. So we're starting with 2.5 molarity for this HF before we have broken apart into these items. Reactants are minus, products are plus, and they all have coefficients of 1. So this is going to be minus x, this is going to be plus x, this is going to be plus x. So we're going to have 2.5 minus x, we're going to have x, we're going to have x. Now, the other important thing here is if they give me a pKa, I need to change it to a Ka. So my Ka is equal to 10 raised to the negative 3.14. If it's helpful, we can plug it in. 10 raised to the negative 3.14. And that's equal to 7.2 times by 10 to the negative 4. So that's what Ka equals. Now see how it's a times 10 to the negative 4? It's been a minute since we've done this. Whenever a K value is times 10 to the negative 4 or smaller, like times 10 to the negative 8, we can make an assumption that makes our math a lot easier. And that assumption is that when we have a K expression, Ka, because this is going to equal concentration of H+, concentration of F- over concentration of HF, right? If this is a really small number, that means that this value is bigger, much bigger than these values, that these x values must be really small compared to this guy down here. Well, and if x is really small, you can neglect it compared to the 2.5 that we can neglect, we can ignore, that 2.5 minus a really small x is essentially 2.5. And then we can plug that in. So instead of doing H+, we can do x. Instead of doing F, that would be x divided by 2.5. So this is going to become x squared. And I'm going to solve for x right now because I want to know what the concentration of H+ is going to be. That's how I'm going to figure out the pH. So I'm going to multiply the 2.5. So 2.5 times by Ka, this is equal to x squared. So if I want to solve for just x, then I do the square root, and that's going to equal my x value. So x is going to equal 2.5 times by my Ka, then I'm going to take the square root of that, 0.042557, just giving myself lots of sig figs here. So at equilibrium, this was 2.5, x is 0.0425, etc., 0.0425. So then how do we solve for the pH? Well, pH is equal to the negative log of the concentration of H+. And guess what? We know what the concentration of H+ is at equilibrium. So then I'm going to plug that in. I'm going to say negative log of this number, of the 0.042557 number. So negative log of that number. Sig fig wise, my starting value was a concentration, and it was 2 significant figures, and then the leading number on a pH value is not significant, so then this would be a 2 sig fig answer for pH. So my final answer is 1.37. Okay, before we continue, if they ask for pH or pOH of a weak acid or a weak base, you need to use an ice table. You're going to always make this assumption that the amount of X that we're removing from this initial is negligible, because our K values are always going to be small enough to make that assumption. From there, you're going to use your K number and expression to solve for X, and that's going to give you your concentration of H+ or your concentration of OH-. From there, you'll do the negative log of that to get your pH, and in some cases, your pOH. All right, let's try this one more time. So find the pH and percent ionization of 1.5 M solution of HCN. So this is an acid. It has hydrogen at the front. It's not one of my big 6, so this is a weak acid. So we're going to be doing an ice table. Let's rewrite our ice table because we don't have to include the liquid water in here. So that means we have the HCN aqueous, and it's going to break apart, equilibrium back and forth to H+ and Cn-. Both of these things are aqueous. The other thing I'm going to need is, instead of a pKa, I need Ka. So Ka is equal to 10 raised to the negative pKa, 10 raised to the negative 9.31, 4.9 times by 10 to the negative 10. All right, and that's a rounded number. So when I dealt with it earlier, I used the longer version. All right, let's make this ice table because it's a weak acid and we're trying to find pH. We're starting with 1.5 molarity, 0 and 0. We got a minus x and a plus x, so it's going to be 1.5 minus x, x and x. Weak acids and weak bases always have a small enough K value that we can make this, like, ignoring exception there. We can neglect that little bit that we're minusing from 1.5. And so then Ka, products over reactants, we don't include liquids or solids, so concentration of H+, concentration of Cn-, all over the concentration of HCN. This is going to be x times by x divided by 1.5, x squared divided by 1.5, 1.5 times by Ka is equal to x squared. So the square root of 1.5 times by Ka is equal to x. All right, 1.5 times by Ka. Notice how I'm grabbing the long number for my Ka, and then square root of that. And so 0.123427, etc. That's what x equals. And so at equilibrium, x is the concentration of H+, right? So to get pH, like we've done, it's equal to the negative log of that concentration of H+. So I'm going to do negative log of that number, the 0.000027 number, and that means pH is equal to, so negative log of that number. Just like before, I see that my concentrations were 2 sig figs. Leading numbers on any p-value are not significant, and so then this would be a 2 sig fig number for my pH. So we have done one of the two things. We just found the pH. Now we need to find the percent ionization. Percent ionization is saying, hey, of this original 1.5 concentration, how much of this actually broke off? Like, what's the concentration of the H+? So if you take your concentration of H+, and you divide it by the concentration of the HA, the original acid here, and then you times it by 100 to make it a percentage, that's where we get this percent ionization. So in this case, it's going to be 0.000027. That was my concentration of H+. I divide it by 1.5. That was my concentration of this weak acid. And I times it by 100. Okay. This is a very small percentage. I'm getting times by 100, I'm getting 0.0018% ionization. Such a small percentage of this actually ionized, actually broke apart. Yep, that looks right. I'm just double checking my math, just see if I saw any issues. I'm wondering right there, I wonder if I have a small calculator error. So we did 1.5 times by, no, I don't think so. And then square root, yeah, we're fine. I think we got it. Double check my work. Let me know in class if I had a calculator error somewhere. All right, here's the last thing we're going to do to wrap this up. Let's try one of these for a weak base, and then we're going to be done. So I'm on page 15. Here's the important thing I need you to know. We talked about it a little bit. When we're dealing with a weak base, water has to be part of this equilibrium reaction because it's the donor. It's actually the acid. It donates the H to the weak base here, this NH3. So that's going to be an important part of this. Just like before, we're dealing with a Kb. So this is my pKb. So to get Kb, we're going to do 10 raised to the negative pKb. And we don't have to like equal this out. We can just plug it in that way. But it's just helpful for my mind when I see it written in more of a standard form. So I get 1.8, etc. times 10 to the negative 5. All right, beautiful. Okay, so I see that it's asking us to solve for pH, not POH. And then when we have nitrogen in the front, not hydrogen in the front, it's almost always, if not always, a base. And then this is not a strong base, so it's got to be a weak base. So you're going to write the equation with a weak base plus water liquid, and then the water is going to lose an H+, and then the weak base is going to gain that H+. And we're going to do an ice table. Now, a reminder, ice tables are for concentrations or pressures, and if something is a liquid or a solid, then we don't have to consider it, okay? Because our equilibrium, our Kb expression, is not going to include that liquid. So it's going to be concentration of hydroxide times by concentration of NH4 plus divided by the concentration of NH3. We're starting with 3.5 molarity, 0 and 0, minus x plus x, 3.5 minus x, x and x. Whenever these acids or bases are weak, their Ka or Kb values are going to be small enough that we can make this assumption that we can neglect the little bit that we're subtracting from it. So then, similar to before, that means we're going to have x times by x divided by 3.5. So x squared divided by 3.5. So to solve for my Kb, 3.5, solve for x using Kb, 3.5 times by Kb is equal to x squared, and then if we take the square root of that, then it will equal x. So 3.5 times by our Kb value, square root 5, so x is equal to 0.007981. Now here's an important thing I need you to know. This is the concentration of hydroxide, not the concentration of H+. So the concentration of hydroxide is equal to x, which is this 0.007981 without considering sig figs. So to get my POH, I do the negative log of that concentration of hydroxide. That will equal POH. Let me run that number. So negative log of this concentration. Again, we were dealing with 2 sig figs, so this would be a 0.97, okay. 2.097, but I want 2 sig figs, which is after here, so I want the 0 and the 9, but the 7 causes it to round up, so then the 9 rounds up, so it's a 2.10. That would be 2 sig figs, but this is not pH, that's POH, and we can assume that it's 25 degrees Celsius because they didn't state otherwise, and we know that 14 is equal to pH plus POH, and our POH is 2.10, so that must mean that 14 minus our 2.1, our pH is equal to 11.9 pH, exactly. Okay, beautiful. That's where we're wrapping this up. So in class, we will do a few more of these. This is how you solve for the pH or the POH of weak acids and weak bases. We're going to need ice tables. We're going to need Ka or Kb values, and on all of these we can neglect the little bit that we remove from the beginning to make our math a lot easier because these K values are so small. All right, everyone, I'll see you in class.